Alright guys, welcome back to Unit 5. So in this video I'm going to finish the rest of the review, Units 5, 6, 7, and 8. Unit 5 was when we really were talking about square roots. So square roots and cube roots. You may want to have a list of perfect squares and perfect cubes on your notes sheet. I know you can't really see that. I'm going to move it. So perfect squares, 4, 9, 16, 25, 36, 49, 64, 81. Perfect cubes, 8, 27, 64, 125, and 216. And that's about all we're going to do for right now. So what you need to do to simplify them is find two numbers that multiply to 175. One of them needs to come from this list. Since this ends in 75, it's pretty easy to tell that it's 25. If you think about how many quarters would be in $1.75, that would be 7 quarters. So 25 times 7, leaving that 3 out there for a second. Then the square root of 25, the whole reason one of them had to come from this list is because these numbers have square roots. So I can do the square root of 25, it's 5. And then it gets multiplied by the 3 that's already out there to make us 15 square root of 7. And that is a simplified square root. For the cube root, I need to find one of these. That goes into 192. And 192 just so happens to be 64 times 3. Then the cube root of 64 is actually 4. So we're going to cross this out and put a 4 out front. Since there's not already a number there, it's just simply 4 cube roots of 3. Done. When you get to questions 4, 5, and 6, you'll notice that there's some pluses and minuses. What you're trying to do is simplify the numbers inside just like that. 48 happens to be 16 times 3. 12 is 4 times 3. And 75 is 25 times 3. What happens now is this is going to become a 4 outside because the square root of 16 is 4. This is going to become a 2 outside because the square root of 4 is 2. And the 25 is going to turn into a 5. So basically I have 4 times 3, 12 square roots of 3, minus 2 times 2, 4 square roots of 3, plus 5 square roots of 3. Since they are all square roots of 3, you can do 12 minus 4 plus 5, which is 13 square roots of 3. On 7, 8, and 9, you'll notice that we got some fractions going on. I'm going to get 7 set up, but then I will solve 8 out of the way. We don't like it when square roots are left on the bottom, so we're going to multiply by the square root of 5 on the top and bottom. Because what happens, and I'm just going to do the bottom, actually, you know what? I'll just solve it. This, when you square a square root by multiplying it by itself, that's just 5 without a square root now. Or this would have become the square root of 25, which is 5. And on the top, we have 20 square roots of 5. And since you can do 20 divided by 5, let's go ahead and do that. That becomes 4 square roots of 5. Because 20 divided by 5 is 4. Number 8 is a little more complicated. Since there is a minus there, what we do is we multiply by what's called the conjugate, which is 3 plus the square root of 5. And then I'm going to go ahead and put this in parentheses as well. On the top, I have 2 times 3, that's 6. And 2 times the square root of 5, that's just 2 square roots of 5. The bottom part gets a little funkier because I have to FOIL this all the way out. I'm going to get 3 times 3 is 9. 3 times the square root of 5 is 3 square roots of 5. negative 5 square root of 5 times 3 is negative 3 square root of 5. And negative square root of 5 times positive square root of 5 is negative 5 without the square root. Because when you multiply a square root by itself, the square root part cancels out. The reason why we did the same thing but just the opposite signs was because this in the middle now cancels out. That square root had already canceled out, and now we just have 9 minus 5, which is 4. The whole point was to cancel out the square root. And then I can divide all of the numbers out front by 2, so I'm going to go ahead and do that. And that is my final simplified answer. All right, let's move on to some of these fractions. I'm going to go ahead and do number 10, 30, and 20. I can divide those both by 10, leaving me with 3 halves. Then, what I'm going to do here is subtract my exponents. This x technically has an exponent of 1. 3 halves minus 1 is 1 half. And then y is going to have a power of 4 thirds minus 1 third, which is 3 thirds, or just 1. Over here, one quick thing, this 1/2 power, when you do the 1/2 power of a number, not another exponent, that is the square root. And the square root of 9 is 3. And then that takes away half of each power. So now the x has a power of 3, and y has a power of 3 halves. Then I go ahead and multiply these two together the same way that I would do it if they weren't fractions. 3 times 3 is 9. 3 plus 2, I have x cubed and x squared, that's 5 x's. And I have y to the 3 halves plus y to the first. 3 halves plus 1, or 3 halves plus 2 halves is 5 halves. And I'm going to go ahead and do 14. This 2 on the bottom stands for the square root of 49, and then it gets cubed. So whatever number is on the bottom becomes the root. Just like I said, this 1/2 power was the square root of 9. This half on the bottom is the square root of 49. It just has a number on top, which means it gets cubed afterwards, which really means we're doing 7 cubed, because the square root of 49 is 7, and 7 cubed is 343. All right, let's talk equations for a second. If you've got two radicals on each side, you just cube both sides if it's a cube root to cancel those bad boys out. Square both sides if it's square root to cancel both of those bad boys out. And if it's anything like these two, where there's only one of them, get it by itself first. And then to cancel out a square root, you square it. That's how you get rid of a square root, guys. So that pretty much just means it cancels out the square root on this side, and 7 squared becomes 49. I will leave you to solve the rest of that equation. I promise you can do it. On 19, you would subtract this 5 to the other side. 8 minus 5 happens to be 3. And to get rid of a cube root, you guessed it, you gotta cube both sides. And that leaves me with 4x minus 1 equals 3 to the third power, which is 27. And then you'll solve these two the rest of the way. For these two, you're just solving x plus 5 equals 2x plus 3. 7x plus 6 equals 2x plus 2. For the bottom part, f of g of x means that you're going to take g of x, x plus 9, and plug it in for x right here. Okay, like that. Then you multiply the two through, or distribute, and combine these like terms. That becomes 2x plus 13. If it was doing this one, you would take f and plug it into g. If it gives you a number, you're going to do f of 8 first, meaning you plug 8 in for x in f of x. So we're changing that x to 8. That's 16 minus 5, which is 11. And then you take that 11 and you plug it into g. So you'll do 11 plus 9. I'm going to star that one because that's actually my full answer. For an inverse, that's what this means. That's where you swap x and y. So I'm going to write this equation, but instead of essentially y equals 2x minus 5, it's x equals 2y minus 5. And I want to try and get y all by itself, so I add the 5 to the other side. And then to get y fully by itself, you divide by 2. So my inverse is x plus 5 over 2. Look at that. Let's go ahead and talk about Unit 6 for a second. And I'm probably going to pause this video after Unit 6 and separate them so that it's not quite so long. Logs! These are my favorite, guys. So when you are solving a logarithm, the answer to a logarithm is the power. So let's say that this equals x for right now. X is the power of 6 that equals 1. Like that. The only power of any number that equals 1 is 0. Then we want to know what power of 27 equals 3. When the number gets smaller like that, you're probably doing a square root or a cube root. I happen to know that the cube root of 27 equals 3. That cube root is a power. It is the 1/3 power, like I just talked about in the Unit 5 video. If the number happens to go to the bottom, 3 squared is 9. The reason why that 9 is on the bottom is because it had a negative exponent. A negative exponent is what makes something go to the bottom like that. So 3 to the negative second power would be 1 over 9, while 3 to the second power is 9. And then let me double check. Little reminder that if there's no little number there, it's automatically a 10. 4 to the first power would be 4. Let's go ahead and talk about some log properties. If two logs are being added together and they have the same base, you are allowed to multiply. So that would become the log of 20 times 5, which is 100. Like I said, it has a little base of 10. So we're looking for what power of 10. 10 to this power equals 100. That's 2. You are always looking for the power of this that gives you this. That's how a log works. If they are being subtracted, then you can divide those two numbers. 54 divided by 2 is 27. And you're trying to find what power of 3 equals 27, which is 3. 3 to the third power is 27. If there is like a triple number thing going on like this extra power can actually be moved out front, and that is the last log property. If they are being added, you can multiply them. If they are being subtracted, you can divide the insides. And if there's an extra power on the inside, you can move it out front. How does that help you? Well, now you can do log base 4 of 16. What power of 4 is 16? 2. There's still that 9 out front because it's getting multiplied. So your final answer here would be 18. Those log properties also get used to expand and condense. See how these are all technically being multiplied together? That means that I would give each one its own log, and there is a little bit of a squish here. They are all added because they were all being multiplied. Same way these were being added, so I multiplied them. These are being multiplied, so I add them. That's expanding. Then, any power you have like this, same thing I did up here, it goes out front. It gets crossed off. Like that. On this one, actually let's go ahead and go down to 18. I've got the ln. It's another type of log. It's called the natural log. So I'm going to put all of these together. Now I'm trying to condense. That means it's already separated, and I'm going to try and make it look like one, like this one. Since these two are being added, we'll do 9 times x, or 9x. Then I kind of get into some weird stuff over here. We've got numbers out front, so I'm going to go ahead and turn those back into powers. Everything's kind of going backwards right now. Since these two are being subtracted, they're going to be divided. And that's a y to the third and a z squared. Basically, I think of it as anything with a minus goes to the bottom, anything that's being added goes to the top. There you go. When you are solving equations in which x is in the exponent, you need these two to both be 5. So we're going to leave the 5 to the 3x because it already has 5. But we're going to change the 25 to 5 squared. Because guess what, guys? 5 squared is 25. Since these two things are equal, I'm allowed to substitute. What that means is now that I have 5 as both of the bases, 3x equals 2 times x plus 3. And I don't care about those stinking 5s anymore. I am going to go ahead and multiply that 2 all the way through. And now I've got a regular equation left to solve. I just need to subtract the 2x to the other side, and I get 1x equals 6. Not too bad. I'm going to get you set up on 21, but I'm not going to solve it the rest of the way. Leave the 7 alone. 49 is 7 squared, but that 49 is not on the top, which means it was a negative second power. And then you would just solve the equation, x plus 3 equals negative 2. You can't cross out the bases unless they're both the same. That's why I substituted on both of those. Go ahead and subtract that 3 over there to solve the rest of the way. What about log equations? If there is the same log on both sides, those cancel. And you're just solving the equation, 7x plus 2 equals 3x plus 14. If two logs are being subtracted, remember that means you divide them. So I have to divide 3x plus 2 by 2x plus 1. I don't know why I did double parentheses there, but it's too late to change it now. This side doesn't change. Now, there's one ln on each side, or one natural log on each side. So those can cancel. People freak out a little bit when they see this one because they're like, this fraction looks crazy. Whenever you're dividing by something and you no longer want to be dividing by it, you multiply it to the other side and you cross it out. So this would become the equation 3x plus 2 equals 8x plus 4. And I'm going to let you guys solve that one the rest of the way out. Over here, because these two are being added, guess what? You have to multiply these two together. So that's going to become x squared minus 6x. Which means we're in a little bit of trouble here, y'all, because that means we have to factor. Whenever you see an x squared, you're going to have to factor that. Now, there's no log over here, so we can't cancel it. What we do instead is we know that this, the answer, is the power of 4 that gives us this. So 4 squared, or 16, equals x squared minus 6x. And then I subtract that 16 so that everything is on the same side. And I need to find two numbers that multiply to negative 16 and add to negative 6. Negative 8, positive 2, leaving me with my final answers, x equals 8 and negative 2. But you can't actually take the log of negative 2, So my only answer is 8. This one is called extraneous. Okay, on the bottom, we have 2 examples of interest. A house bought for $50,000. So start with 50,000. Has increased in value 3% per year. Since it has increased, you're going to do 1 plus the rate. But remember that you need to do 3 divided by 100 to get the decimal form. Do not plug 3 in. Then you're giving somebody 300% interest rate. That's crazy. Okay? So then it says, what value will the house be in 2002? It was bought in 1980, so 2002 is 22 years later. Okay? It basically starts with your initial amount times 1 plus the rate to the power of time. Okay? Then you would type that into a calculator. I'm not going to do that right this second. I want you to practice that and check the answer key. Here, the Kia Sorento is starting at $27,500. And it's decreasing. Only difference is instead of 1 plus, we're going to do 1 minus. 7% as a decimal is 0.07. And it wants to know how much it's going to be worth in 5 years. Type those bad boys into your calculator and you are good to go. And I'm actually going to go ahead and push through and go for Unit 7 really quick. Okay, for Unit 7, rational expressions. Factor. Got to factor. Okay, I'm going to start with, let's see, I'll do this one, and I'm going to set up this bottom part of the factoring for you. So if you ever see 2 things alone like this, and one of them is x squared, this is called difference of squares. It's going to turn into x plus 3, x minus 3. On the bottom, I can divide these both by 8. That's called a GCF. And what happens is you put it out front, and then you divide by 8. 8x divided by 8 is x. Negative 24 divided by 8 is negative 3. And then everybody's favorite part of math, crossing things out, it's x plus 3 over 8. Okay, I'm going to go over how to factor this bottom part. The top part is 2 numbers that multiply to 40 and add to negative 13. That is negative 5 and negative 8. On the bottom, though, you have to find 2 numbers that multiply to 3 times negative 5, which is negative 15, and add to negative 14. That's negative 15 plus 1. And what happens is you actually have to split that up like this in the middle. So instead of the negative 14x, you replace it. These 2 pieces are the exact same as up here, though. Those don't change. Then you do what's called factoring by grouping. I talked about this in the Unit 3 video. You can divide these 2 by 3x, and you have x minus 5 left. You can divide these 2 by 1, and you have x minus 5 left. So the factors for this part are 3x plus 1 and x minus 5. And I can cross off, it's kind of hard to see, I know, the x minus 5 from the top and the bottom. And I have x minus 8 over 3x plus 1 left. Okay, now let's talk about adding. You have to have a common denominator. Please get a least common denominator first. Do not try and factor until you have one. It's going to get very, very tricky. Like on this one, I don't need to factor this up here yet. I only need to factor this bottom part. Negative 9 times negative 1 is 9, and they add to negative 10. The important piece here is that I need to then see what's missing to get a common denominator over here. The x minus 9 is missing. So I multiply by that on top and bottom. so that now I can make this one big fraction with the common denominator. What I'm going to do as I do that is multiply this 6 all the way through. That makes 6x minus 54. And I'm going to add 6x and negative 7x, negative 18 and negative 54. The x squared doesn't have any like terms. Negative 7 plus 6 is negative 1x. And negative 18 minus 54 is negative 62. Now I need, negative 72. Knew that sounded off. I need two numbers that multiply to negative 72 and add to negative 1. That's negative 9 and 8. And I keep my common denominator there. So I get my common denominator so I can make these two into one fraction. Then I factor the top part so that something can cancel out. And that is my answer. A very, very, very similar idea happens with these rational equations. You are going to multiply just the top parts by the LCD. Let's see, which one do I want to pick? Let's go with the middle one again. So in order to see my LCD, like I did up here, you have to factor the denominators. This one's good to go. This one's good to go. Two numbers that multiply to 8 and add to negative 6 are negative 4 and negative 2. So my least common denominator is this, because it's just these two put together. So I'm going to multiply by that on the top of every fraction. And I know that's kind of hard to see, but I'm just writing this on the top of every single one. Now, here's the cool thing that happens. On this first one, the x minus 2's cancel, so I just have 2x minus 4. Then I have my plus sign, and my x minus 4's cancel, so I have x times the x minus 2. And over here, the whole thing's on the bottom, so that all cancels, and I just have that 2x plus 7 that was already there. Then I got to distribute. That's going to become 2x minus 8. This one's going to become x squared minus 2x. And here's what I'm going to do. I need to minus the 2x over to this side. I've got 2x minus 2x minus 2x. 2 plus negative 2 plus negative 2 is negative 2x. The x squared stays. And I need to subtract the 7. Negative 7 and negative 8 make negative 15. For my finale, I need two numbers that multiply to this and add to this. That is negative 5 and 3. So my two answers are x equals 5 and negative 3. They always flip after you factor. Okay, let's talk about rational graphs for a second. Same thing as I just said up here with these, you have to factor and simplify first. So two numbers that multiply to 8 and add to negative 6. We've actually already done this one. It was negative 2 and negative 4. On the bottom, what multiplies to 2 and adds to negative 3? Negative 2 and negative 1. Then look for something you can cancel out. As that cancels out, it leaves behind what's called a hole. The 0 of that factor would have been 2. To figure out how high or low to put that hole, you plug 2 into what's left, which is x minus 4 over x minus 1. So it would turn into 2 minus 4 over 2 minus 1. which is negative 2 over 1. So my whole is at 2, negative 2. Over 2, down 2. And notice how I made it an open circle, because again, it is a whole. For the x-intercept, that is when you set the top equal to 0. So if I set x minus 4 equal to 0, I would add the 4 to the other side. That's my x-intercept. The vertical asymptote is when the bottom part equals 0. This one is a dashed line because this isn't actually allowed to be 0. If I set it equal to 0, I would add the 1 to the other side, and it would be at 1. So I go to where x equals 1, and I draw a vertical line. X isn't allowed to be that because we're not allowed to divide by 0 in math. For the y-intercept, you plug in x equals 0, which would be 0 minus 4 over 0 minus 1, which is negative 4 divided by negative 1. That's 4. There it goes. And the horizontal asymptote has two rules. If they are the same power on top and bottom, it's at y equals 0, y equals the numbers in front divided. If it is different powers, it is y equals 0. So I have the same power on top and bottom, so I have to divide the numbers in front, which would be 1 divided by 1. 1 divided by 1 is just 1. So that's going to be a horizontal line at 1. And that splits my grid, and these curves just get close to the asymptotes like that and like that. All right, Unit 8, last one. I know I said I was going to go all the way through it, but then I decided to power through for you guys. Okay, I'm going to do one of each, y'all. Circle, ellipse, and hyperbola. Notice how parabolas aren't on this list. For a circle, your center is these two numbers, but they both have to be the opposite. So our center is actually going to be 1, negative 3, instead of negative 1, 3. Boom. The radius is the square root of this number, which is 2. So you go 2 in every direction, and you draw yourself a circle. Done. For the ellipse have a plus sign in between. A hyperbola would have a minus sign in between. For an ellipse, your center is the same kind of thing it was with the circle. These two numbers, 4, 3. Over 4, up 3. Then in the x direction, you're going to go over 2, because the square root of 4 is 2. Right and left. For the y value, the square root of 9 is 3. So up 3 and down 3. Then draw yourself your ellipse. Whichever one is longer. These are the vertices. So that's over 3 up 6 and over 3 up 0. So 3, 6 and 3, 0. The shorter one on an ellipse is the co-vertices, which is over 2 up 3 and over 6 up 3. So 2, 3 and 6, 3. For the foci, you need this equation. C squared equals A squared minus B squared. So you just subtract these two numbers. 9 minus 4 is 5. And then you do the square root. Okay. The square root of 5, double checking this decimal really quick, is 2.2. So you would go on the longer direction, up 2.2 and down 2.2, which puts me over 3, up 5.2, and over 3, up 0.8. That's an ellipse. Longer one is vertices. Longer side equals vertices. On a hyperbola, same kind of setup, but the first one equals vertices. Doesn't matter which one's longer. And for this one, your foci are a squared plus b squared. Okay? So the center on this one is actually the exact same as it was up there. I kind of made these two similar on purpose. There we go. Then my vertices are the first one. So my x's are going to go over by 2, just like they did on the last one, because it's the same kind of equation. So that's 2, 3, and 6, 3. Graph them first, please. That helps a lot. Then for my covertices, the square root of 9 is 3. So I go up 3 and down 3, because that number is underneath the y. And then I make a box out of my vertices and my covertices. And those 2 points I just drew, oops, got a little ahead of myself, are 3, 0 and 3, 6. Then you draw your asymptotes through the diagonal of that box. That is the whole reason we draw the box, guys. Whichever one goes first, whichever one has the vertices, gets the curve. Meaning that I'm going to draw the curve here and here. Here and here. Then, for my foci, instead of subtracting them like I did on the ellipse, I have to do a squared plus b squared. So for plus 9, which is 13. And then I do the square root of 13, which is 3.6. So I go back to my center and I go left and right 3.6 because I'm going in the direction of the curve, which puts me at 0.4 up 3 and negative 7.6 up 3. Sorry, 7.6 up 3. And there you have it. That's the last half of the review, guys.